In this section, we talk about the divergence theorem of a vector and a matrix. Okay, but we first talk about the divergence theorem of a vector. It is easy because such kind of theorem have been learned before in your class of in other class of engineering mathematics. Okay, suppose we have a vector u here. We integrate it over a surface with a area vector dA. Okay, let us look at the geometrical picture here. For example, in the three-dimensional space, we have a closed surface. On this closed surface, we have a unit outer normal, little n, and also we have a area vector dA here. Okay, and then the length of this vector, represent the scalar of the area here, because we have a small area here. How small? How large? The length, the size of the area equal to the length of this vector. Okay, and then we want to use this vector here. We put this vector here and then take the inner product with a vector, and then this vector can be replaced by this one. Okay, because dA equal to n vector dA. This dA is just the absolute value, the norm of this vector, and then the little n is the unit outer normal equal to this divided by this. Okay, so this one can be replaced by this one, and this one is just this. Now, according to the divergence theorem, this vector can be replaced by the divergent V, and this surface integral can be replaced by the volume integral. Okay, and what is divergent V? Divergent V is this one, divergent V. Partial u1, partial x1, partial u2, partial x2, partial x3. Okay, and then in the index form, this one equal this one, and then the inner product can be written as this way. Now the index I is repeating, so we can sum it over 1 to 3. Okay, u1 n1, u2 n2, u3 nv, and sum together. And then this divergent term can be expressed as partial ui, partial xi. Since I is repeating, so we sum this term over 1 to 3. Okay, this is the traditional notation for the vectors and the inner products. Okay, now we learn something new. What news? If we turn this vector into a matrix, what happened? Divergence theorem for a matrix. Look at a stress matrix. Okay, this is the stress, and then this is the unit outer normal. This is the Cauchy traction formula, where we have this one. We have talked about this before, and then now the traction equal to the stress tensor, matrix times the unit outer normal. Now we define our stress matrix by three vectors. This row vector, this row vector, this row vector, they all can be denoted as sigma vector bracket 1. Okay, sigma vector bracket 3, sigma vector bracket 2. Okay, this T denote the transpose, because now the vector is in horizontal, not in the vertical direction. So we put a transpose here. Okay, so now in this way, the stress matrix can be divided into three vectors. Okay, one vector, two vector, three vectors. Okay, and now we carry out the multiplication. This one multiply this equal this. This one multiply this equal this. this one multiply this equal this. Okay, that's the inner product. Okay, this vector inner product with this is this, and this one times this one is the inner product, the vector inner product n. Okay, and then this, now after the inner product, this is a scalar. Okay, and this scalar can be put in this way. Okay, this scalar equal to T1, this scalar T2 equal to this scalar, T3 equal to this scalar. Okay, so now we have a more convenient form to work with. Now we consider the surface integral, surface integral of the traction. We integrate the traction all over the surface. Means that we are looking for the resultant force. Of course, resultant force will be zero for the equilibrium state. But now we focus on the mathematical part. We integrate this vector all over the closed surface, and then we replace t by this one. And then now this one can be replaced by this one, because this one is this one, right? So this one is this one. Okay. Now we integrate this vector to on the surface. Now we perform the integration to each component. This component, this component, this component. So we move this one to here to get this one. If we integrate this component like this, integrate this component like this. Okay. And now for this term, this is a vector. Understand, this is vector. This is a unit outer normal. So we can apply the divergence theorem for a vector directly. This is the u vector. Take it as u. U vector n and dA. What happened? U vector n and dA. What happened? Equal to the divergent v and the volume integral. Okay. So this vector u vector n dA surface integral turn to the volume integral and divergent u vector, if this is u vector, right? So we can this equal to this, divergent this. Okay, and this is the volume integral. In the same way, this can be replaced by this. This can be replaced by this. Okay. Now we write our term like this one. Okay. And then this vector, low vector means that this is the stress matrix, right? Means that low vector. So this is the stress matrix. Okay, this one. So we put it like this. Divergent stress matrix. Okay, so let us summarize our result. Means that this one, the stress matrix times the unit outer normal n, and then integrate over the surface like this, will be equal to the volume integral of divergence sigma here. And what is divergence sigma? Divergence sigma is here. Okay, we have three components of the vector. Okay, divergence sigma. Now in this whole expression, this one can be replaced by this one. Sigma n equal to sigma ij times nj, and then this just equal to ti. Okay, sigma ij nj equal to ti. Okay, this is just t vector, and then this divergent v, divergence sigma equal to sigma ij comma j. Comma is the partial differentiation. Okay, and then replaced by this one. Okay, in this way we can carry out the divergence theorem to the stress matrix. Okay. We will make use of this result later.